You ever ask an AI a question and get an answer that sounds brilliant but is just completely wrong? Yeah, we've all been there. But what if AI could have a perfect, verifiable memory? Well, today, we're going to pull back the curtain on something called Retrieval Augmented Generation, or RAG for short. It's the architecture that's making AI way more reliable.
So here's the core problem, right? Even the most powerful large language models, the LLMs, they have this fundamental flaw. All their knowledge is static. It's basically frozen at the moment they were trained. That means no real-time info, and even worse, they can hallucinate. And I mean, they literally just make stuff up when they don't know the answer. And this, right here, is the solution in a nutshell. Over on the left, you've got your standard LLM. It's like an isolated brain. But on the right, that's a RAG system. The best way to think about it is that we've given that brilliant brain a library card to an infinite library. Suddenly, it can connect to external, up-to-the-minute knowledge, grounding its answers in facts you can actually check.
Okay, so how do we actually build this thing? Well, the first huge engineering hurdle is, how do you teach a computer to read and, understand all that human knowledge in its new library?
The magic trick here is something called a vector embedding. It's a process that takes any piece of text, a word, a sentence, a whole document, and turns it into a special list of numbers. We call that a vector. Now, the really cool part is that texts with similar meanings end up with mathematically similar vectors. It's like creating this super detailed index card that doesn't just capture keywords, it captures the actual essence of the text.
Let's see how this all builds up from scratch. It all starts with a scalar. That's just a single number. A list of those numbers becomes a vector, and that vector represents one chunk of text. Then, a big batch of all those vectors together is called a tensor. These are the literal building blocks of the AI's memory, taking us from a single value to this incredibly complex map of knowledge.
And just how detailed are these index cards we're talking about? Get this. A high-performance embedding vector today can have 3,072 dimensions. Each one of those dimensions is capturing some tiny different nuance of meaning. That's a level of granularity that is just mind-boggling. It lets the AI understand concepts with absolutely breathtaking precision.
Okay, so we've turned millions of documents into these super complex vectors. Awesome. Now for the next challenge. A user asks a question. How in the world do you find the one right vector, that one needle in a massive haystack of information, almost instantly?
Well, the most popular method is called cosine similarity. Now, instead of measuring the straight line distance, it measures the angle between the user's question vector and all the document vectors. What's crucial about this is that it doesn't really care how long a document is. It only cares if it's pointing in the same conceptual direction. It's pretty much perfect for finding things that have a similar meaning.
But, sometimes you need a different tool for the job. Euclidean distance. This one measures the direct, straight-line path between two vectors. It's much more concerned with magnitude, which makes it super useful when things like word frequency or other kinds of count-based data are what's really important for your search.
This table here sums it up perfectly. If you're doing semantic search, trying to find similar meanings, engineers are almost always going to use cosine similarity. But for other tasks, like grouping similar data points together, they might go with Euclidean distance. Picking the right search method is a huge engineering decision that totally changes the quality of the AI's research.
All right, we've found the right facts. Now comes the really artful part. How does the LLM take these raw bits of text it just found and weave them all together into an answer that sounds coherent and, human?
You'd think that as long as the AI has the facts, it can figure it out. But here's where things get really subtle and kind of fascinating. It turns out the order in which you give those facts to the AI can dramatically change how well it performs.
Yeah, this is what researchers call the lost in the middle problem. Studies have shown that LLMs have this weird U-shaped attention span. It's because of their deep mathematical architecture, specifically a thing called rotary position embeddings, that they pay the most attention to information you give them at the very beginning and at the very end. Anything you bury in the middle tends to get a lot less weight.
And we're not talking about a small dip here. Accuracy can absolutely plummet by over 30% if the most critical piece of information is stuck in the middle of the context. This is exactly why context engineering, strategically arranging those facts, has become one of the most important jobs for getting a reliable answer out of these systems.
So we've figured out how to read, how to search, and how to weave it all together. But that leads us to the final, and honestly, the most important challenge of all. How do we know the whole system is working? How can we actually trust it? Well, the industry has kind of standardized around this framework called the RAG triad. The easiest way to think about it is as a simple 3-point checklist you can use to grade the reliability of any RAG system.
First on the list is faithfulness. This is your anti-hallucination check. It asks one simple question. Is every single claim in the final answer backed up by the documents the system found? If not, it fails. Simple as that.
Second, you have answer relevancy. Look, the answer might be factually correct, but does it actually help the user with their original problem? This metric makes sure the AI doesn't just go off on some tangent or give a half-baked response. It's all about user satisfaction.
And third is context precision. This one zooms in on the performance of the retriever itself, the AI's little research assistant. Did it actually pull the best possible sources from that library? And did it put the most important ones right at the top?
And this is where it all clicks into place. This table shows you how these abstract ideas connect to very real-world stakes. A failure in faithfulness isn't just a wrong answer. It could be a serious clinical or legal safety problem. A failure in relevancy just frustrates users, and poor precision wastes a ton of computer power and money. This triad isn't just for developers. It's a framework for business leaders and safety officers.
So let's bring this all down to earth and look at the practical trade-offs engineers have to make every single day when they build these systems. Because it is a constant balancing act between getting the best performance and, well, how much it costs.
This chart shows a classic engineering trade-off. Using those big, super detailed embeddings gets you much better precision, but as you can clearly see, it also makes your search time go way up. So a smaller, faster model might be perfect for a real-time chatbot, but you'd probably want that slower, more precise model for high-stakes medical research.
And this table here lays out to cold, hard numbers. Yeah, moving to a larger vector size gives you this huge jump in precision. We're talking from 0.65 to 0.91, but look at the cost. The amount of storage you need for every million documents balloons from 1.5 gigs all the way to 12. Every single engineering team has to look at this and decide, where do we want to land on this spectrum between cost, speed, and quality?
So at the end of the day, RAG has become so much more than just a clever technique. It's really become the core infrastructure for building AI that's reliable, that you can audit, and that's ready for the enterprise. By grounding these powerful models in facts we can verify, it basically solves their single biggest weakness. And that leaves us with one final thought. Is this just another tool in the AI toolkit, or is it actually the foundational blueprint for a future where we can genuinely trust our AI?